Okay, so hi everybody. Welcome back to the Topos Institute Colloquium. Today we're very excited to have a talk from Maru Sarazola about double categorical equivalences. So please, whenever you're ready, take it away.
Yeah, thanks so much, Evan. And thanks for the invite to speak here today. I'm always happy to get invites, but I'm particularly happy to talk about this project here at Topos because I know that the Topos crowd has been doing really exciting work with double categories. So I think that maybe some of the things in this project will resonate with some of you. That's my hope, at least. All right, so what I want to talk to you about today is this project that we have together with my collaborators Lynn Moser and Paula Verdugo, which is called Double Categorical Equivalences. And it's kind of predicated on the following motivating fact, which is that categorical structures come with a canonical notion of equivalence, right? So just to illustrate this with some very familiar examples, if we talk about categories as our structure, the canonical notion of equivalence we know is equivalence of categories. And if we do two categories, then we have the bi-equivalences of two categories. And what I want to focus on today is what should go in the third slot here in this table if the structure that I want to consider is a double category instead. So what should be the canonical notion of equivalence between double categories? So just to do a super quick recap, I think you're all likely very familiar with these structures, so I'll go kind of fast, but please feel free to stop me and ask me any questions. So a two category has objects, morphisms between these objects, and two cells between parallel morphisms, so they look like that. And then kind of in contrast, a double category, so this is going to be another two-dimensional structure. It's going to have objects, but now we have two different types of morphisms, which I'm going to denote as horizontal morphisms and vertical morphisms. Not that there's anything inherently horizontal or vertical about these. This is really just to think of them as like living in different dimensions. They may or may not have anything to do with each other. And the way in which these horizontal and vertical morphisms interact with each other is via our higher dimensional cells, which are given to us in the form of squares. So maybe the clarification that is important to make is that everything is strict today for the purposes of my talk. So in a double category, horizontals and horizontals compose with each other. They are strictly associative. There's a strict identity. Same for the composite of vertical morphisms and vertical morphisms. So everything will be strict. All right, so these are kind of the structures that we want to keep in mind. And now our question is, what's an equivalence of double categories? So I'm going to try to approach this problem by mirroring what we have for two categories, right? It feels like I should be able to write down explicitly what it means to have a bi-equivalence and then try to copy as best as I can, or maybe translate what that would mean if I pass to double categories. So for two categories, if I have a strict two functor, I say that this is a bi-equivalence if it satisfies the following conditions. So it has to be surjective on objects up to equivalence, by which I mean for all objects B in the target, I need to have an A in the source and an equivalence between f of A and B. They have to be full on morphisms up to iso 2 cell, and they have to be fully faithful on two cells. So this is our usual notion of bi-equivalence between two categories. I'll just repackage this information more succinctly in this first column here. And maybe what I will remark before I go on to the double categorical setting is I just highlighted this word equivalence. I just want to make sure we all understand there's nothing circular going on here. The highlighted equivalence is an internal equivalence to my two category, right? So this notion of equivalence is it's a morphism in my two category, let's call it F, such that I have a morphism in my two category pointing the other way, let's call it G, and I have iso 2 cells that relate their composites to the identity, right? So every two category that I get comes equipped with a class of these equivalents kind of naturally by the data that it contains. All right, so what happens if I try to just naively translate this definition? So now if I have a double functor between double categories, I will say it's an equivalence if, all right, so the first item was surjective on objects up to equivalence on the two-cat side. So now I will say surjective on objects, but my question is up to what? And this is already not an obvious thing to answer. Because the fact that I have two different types of morphisms in my double category gives rise to choices of surjectivity that I could be asking for. So for instance, I could be saying it's surjective on object up to a horizontal equivalence, or maybe up to a vertical equivalence, or maybe I want to ask for both horizontal and vertical equivalences. Maybe if I ask for both, they should be satisfying some kind of compatibility between each other. So you can see how there's several possibilities as to how I could start to complete this table. And this is pretty much the crux of this issue, right? We're after a canonical notion of equivalence. So we know this should not involve any choices, right? I'm supposed to be finding something that stands out as the most natural thing for me to do, and I shouldn't be choosing something over something else. All right, so just to clarify this quickly, the notion of horizontal and vertical equivalences does exist. So that's not an abstraction at all. Copying that part over is super easy. For instance, if you want to think of a horizontal equivalence, that's a horizontal morphism with another horizontal morphism pointing the other way, and with vertically iso squares like so, where three of these boundaries in the squares are all identity maps. So it's not that, it's very easy to come up with the definitions of internal equivalences. The question is, which ones should I be considering for my surjectivity? Okay, so before I tell you kind of the notion that we're going to try to push for in our project, I just want to really quickly mention that there's also other things that I could try to do. So my strategy today was I'm going to put up the definition for two categories and I'm going to translate as best as I can, but I could be taking other approaches to this problem that are also pretty reasonable. So for instance, I could remember that double categories are categories internal to cat, and I could leverage my notion of equivalence in cat to get a notion in the internal setting. So I could ask that a double functor is an equivalence if it gives me equivalences of categories between the underlying category of, say, objects and vertical morphisms and the underlying category of horizontal morphisms and squares. So these F0 and F1s would just be equivalences of categories. So it's certainly something that's available to us. Here's another perspective I could possibly take. So whenever you have a two category, there's a result by Lack that says you can always construct a model structure on the underlying one category in which the equivalences of your model structure are these internal equivalences that come in the data of your two category A. So this is something you can do for any nice two category. So we could specialize this result to the two category we get by considering as objects double categories, as morphisms double functors, and as two cells, let's say horizontal natural transformations, right? So the data of the category of double categories can actually be repackaged into a two category. And I could just apply the generic result that I just cited by Lack. And if we specialize it to this specific A, we will be saying that a double functor is an equivalence precisely if there's an opposite double functor together with horizontal natural isos between the composites and the identity functors. So this also seems like a reasonable thing to do. I'll just point out one last thing we could do, which is that whenever you have a two category A and a two monad on A, you can put a model structure on the category of T algebras whose equivalences are just whatever algebra morphisms that are underlying an equivalence in the 2 category A. So this is yet another thing you could do. And again, you could specialize this to double categories by recalling that we can see double categories as the algebras for a certain 2 monad over the 2 category cat graph. So I don't want to be more specific about this because I'm not really going to use this, but I just wanted to highlight there's several things that one could try. And all of these 3 perspectives I just outlined, these are all studied by Fiore, Pauli, and Pronk in a really beautiful paper from about 10 years ago. And they're all really interesting and, more importantly, really relevant, right? All these perspectives that I mentioned were quite natural. However, none of these are quite what we are looking for. And let me tell you why. All of these notions, if you actually sit down and write down all the details and unravel what they will give you, let's say just even at the level of objects, the kind of essential surjectivity that you will be getting is up to ISO. It's not up to equivalence. So these notions are kind of inherently one-dimensional in some sense, and they're not really seeing the entire two-dimensional nature of our double categories. So to give you a concrete example, this will be like taking one of these notions as our equivalences of double categories will be like saying that our bi-equivalences of 2 categories are surjective up to ISO. And we just know from experience that that's really not what we want. So we're looking for something that's inherently two-dimensional. And that's kind of why we need to approach this problem in a slightly different way. All right, so just to repeat, our goal is to find a canonical notion of equivalence between double categories that doesn't require making any choices. And the approach that we took to this problem, the way that we solved this, is to use homotopy theory. So I think this project it's pretty exciting. We're really happy about it. You know, in part because of the actual categorical results that we're getting, but also because it illustrates how you can use homotopy theory to inform category theory. Like very often, the information flows in the other direction. But this is an example where we have just a categorical problem that's not so easy to resolve purely within the realm of category theory, but maybe with some tools from homotopy theory, it can help us out. All right, so what do I mean when I say we're going to use homotopy theory? I'm going to make 2 assumptions, and I'm just going to kind of take these as a given, right? So I'm not going to justify these much further. These are going to be my axioms in a way. Hopefully they're not going to be too controversial, but here they are. First of all, we're going to assume that any good notion of equivalence that we ever come up with has to be part of a model structure on the category of double categories. So for those of you who are maybe not as familiar with model structures, this is like a homotopical structure that you put on a category. And the reason why assumption 1 is reasonable is that experience has taught us that this is always the case, like again and again. You have a notion of equivalence, you can, with some effort, fit it into the class of equivalences in a model structure on that category, especially for a category as nice as double cat. So I'm just going to assume that this is going to be the case for any reasonable notion that I can come up with. And this is kind of backed by the fact that this indeed happens for our other 2 motivating structures. So for categories, there's the model structure whose weak equivalences are the equivalences of categories. This is due to rest. And for 2 categories, we have the similar result for by equivalences. This is due to work by lack. All right, so that's my first assumption. The upshot of making this assumption, because of course it's going to restrict things maybe in theory a little bit, but now if we assume kind of with foresight that we will have a model structure, there's a lot more things that we can pay attention to. And I want to highlight some of those things in the following table. So the main thing you'll need to know about model structures really for the main goal of today is that, as I said, it's a homotopical structure you put on a category where you highlight important classes of maps. So the most important of these classes is your class of equivalences, but there's also these auxiliary classes that are lying around and that help you figure things out in the model structure. And one of those is called trivial fibrations. So any model structure comes with a class of trivial fibrations. This is a subset of the equivalences, but they're usually better behaved. For example, if you pop up the hood of the model structure for cat and you look at who the trivial fibrations are, you find that it's the subclass of the equivalences of categories for which the surjectivity on objects happens on the nose, right? So before we had surjective up to iso. For a trivial fibration, we have surjective, like literally surjective, up to equality. If we go to Lack's paper and we see who are the trivial fibrations for two categories, it turns out that it's a very similar situation where the extra condition you put on the biequivalences is that they're not just surjective on objects up to equivalence, they're surjective on the nose, again, up to equality. So the reason why this is particularly handy to us is that remember that all of the choices we were forced to make in the double categorical setting were coming from the different options of essential surjectivity that we could be asking for. However, if we put a pin on the weak equivalences for a moment, those are maybe out of reach right now, but focus instead on who the trivial fibrations for double categories should be. With our strategy of mirroring what we have for cat and 2cat, there's no choices to be made. So the fact that we have this strict surjectivity eliminates the choices and gives us a canonical notion of trivial fibration, where we have surjectivity on objects on the nose, they have to be full on horizontal and vertical morphisms, and fully faithful on squares, because these conditions were easy to translate and required no choices from the beginning. Okay, so if we're kind of convinced that this seems to be a good game to play, I'm going to add our second and final assumption, which is that this class of trivial fibrations that we just identified in the table have to be the trivial fibrations in the model structure that we eventually produce. So assumption 2 is that these should be what we're going to call the canonical trivial fibrations, meaning when I come up with my notion of canonical equivalence, by assumption 1, they will be part of a model structure. Assumption 2 is telling me who the trivial fibrations in the model structure should be, because these seem to be a good starting point. All right, so now under these two assumptions, we're going to try to tackle our problem. And the nice thing is that now we can use some homotopical tools from model structure world to study maybe all model structures on double categories with these canonical trivial fibrations. Because at this point, we don't yet know who the equivalences should be, but we have agreed that these will be the trivial fibrations. So maybe there's things that we can say at this point, even without the knowledge of the equivalences. And it turns out there's quite a bit that you can say. So maybe if you're not super familiar with model structures, I'm afraid I'm going to lose you for a couple of slides. I'll let you know when we come back to our fully categorical problem. But for those of you who have seen these structures before, let me point out a couple of really cool things. The first one is that it's quite, so first we said these all have the same trivial fibrations, which means by model structure abstract nonsense, they will all have the same cofibrations. This is another important class of maps that are part of the structure. These are completely determined always by the trivial fibrations. So any model structure like this that I could put will have the same cofibrations, and it's very easy to find the generating set. So it's easy for me to identify 5 cofibrations such that taking certain co-limits and composites of these, I will cook up my entire class. So the way that you do this, it's actually pretty simple. You look at your description of the trivial fibrations, which we have a very explicit description. It does this to objects, this to horizontal and vertical morphisms, and this to squares. And you separate each of those conditions and you try to find exactly what is the double functor such that a lifting property against that double functor will give you that precise condition. So you find that surjectivity on objects amounts to lifting against this map I1 that I drew. Fullness on horizontal morphisms amounts to lifting with I2, and I3 will give you vertical morphisms. And then I4 and I5 capture separately the full on squares and faithful on squares. So it's easy to extract this very small generating set. And now that we understand the trivial fibrations and the cofibrations, we can prove this really technical result, which says any model structure on double categories with these canonical trivial fibrations has to be left proper. So left properness in a model structure talks about certain pushouts behaving well. So you're saying whenever you have a pushout of an equivalence along a cofibration, you produce an equivalence. That's not a trivial thing that you get for free in a model structure at all. But we can kind of boil down that statement from talking about pushouts of equivalences to only talking about trivial fibrations in this specific example, which allows us to fully prove this result, again, even without knowing who the equivalences are. All right, so end of the model structure technical bit. Maybe if you zoned out, this is a good time to come back to our main goal, which is to complete this missing space in our table. Who should be the canonical equivalences of double categories? So what we're going to try to argue is that these should be the gregarious double equivalences. So I'm going to tell you who these are. I'll define them for you in 1 minute. But I want to make it abundantly clear that here we're not coming up with a new notion of equivalence of double categories for the canonical ones. We are rather finding these in the literature. These were put forth by Campbell about 5 years ago. And we are going to kind of champion these as what we should all agree are the canonical notion for double categories. So in fact, for those of you familiar with when these were introduced, what I'm saying should not be a coincidence at all, because Campbell put these forth exactly to serve this purpose, right? And in the talk that he gave, it was originally called the folk model structure on double categories. So he knew this all. This was certainly the reason why he introduced these. And what we're going to try to do is use our tools to really back up his claim that these should be the canonical ones. All right, so let me tell you what these equivalences look like. And that requires me to tell you what a companion pair is. So if I have a double category, a companion pair is the data of two morphisms. So I have a horizontal morphism F and a vertical morphism U. They have to share the source A, right? So they have to form kind of a corner of a square. And the companion data tells me that if I complete both of those squares that I could form with the identity maps, I need to have the data of squares filling in those cells such that when I compose those squares in the only two possible ways, they give me the identity. So it seems kind of technical if you haven't encountered this notion before. So let me maybe just give you a slogan. The way that you should think about these is this is the closest that we can get in a double category to thinking of the horizontal morphism F as having a vertical counterpart, which will be the U, right? So as we said formally, horizontal and vertical things live in different dimensions, so it would make no sense in general for me to say that F is also vertical. But this is the closest that I can get. It's like up to an iso square, it's also vertical. That's what these companions are trying to tell you. And of course, this notion is completely symmetric, so it allows you to think of the vertical morphism U as having a horizontal counterpart in F. Okay, so with these companion pairs, one can define what it means to have a gregarious equivalence. And this is going to be an internal notion of equivalence inside of a double category. So this is not yet an equivalence between double categories. This is just internal to a specific double category. So a gregarious equivalence is going to be a companion pair in which the horizontal map is a horizontal equivalence and the vertical map is a vertical equivalence. So note in particular, if you allow me to go all the way back to when we presented a bunch of different options for the kind of surjectivity that we could ask for, this would look like the third option, where we have both a horizontal and a vertical equivalence that form a corner. But additionally, the companion data is telling you that this horizontal equivalence is pretty much the counterpart of this vertical equivalence that we have. So it's not just any random horizontal and vertical, they are very closely connected. So that's exactly how Campbell defines the gregarious equivalences, which we're terming gregarious double equivalences in our paper. So now a functor between double categories will say it's a gregarious double equivalence if it satisfies the following. So the surjectivity on objects will now be up to gregarious equivalence. So like we said, we have both a horizontal and a vertical equivalence like so in a corner, plus all the compatibility given by the companion. And then we have the notions on horizontal and vertical morphisms and squares, as we had already guessed from the beginning. We have fullness up to a globular isosquare and fully faithfulness on squares. These, as we said, are just the direct translation from the 2-cat case and required no choices whatsoever. Okay, so this is the notion that we're claiming should be the canonical equivalences of double categories, but perhaps so far, I mean, they do seem really natural. It's nice that you're asking for surjectivity both in the horizontal and the vertical direction, but at this point, one could still ask, like, how are you sure that this is the right choice? It seems like we're still making a choice. We're also maybe making a choice on what exactly is the compatibility that they should have, because maybe it's via these companion squares, but it could be some other kind of compatibility. So how can we be sure that these are canonical? Well, this is going to come from our homotopy results. So first of all, we just make sure that these gregarious equivalences fit into our homotopical story. And in fact, they do, because there is a model structure on double categories having these as weak equivalences. So that was fulfilling our assumption 1. And having the canonical trivial fibrations as the trivial fibrations. So that fulfills both of our assumptions. So this is a good example for us. So now that we know that it fits into our assumptions and into our homotopical story, how can we justify our claim about them being canonical? Well, we prove this result that says any model structure on double categories with this chosen class of canonical trivial fibrations, so anything satisfying our assumptions, must be a Bowles field localization of the gregarious model structure. So for those of you familiar with model structures, these are familiar words, but let me explain in kind of layman terms, what does this even mean? So what does it mean to have a Bowles field localization? The important thing you should take away from this result is that this implies that the gregarious double equivalences are the minimal class of equivalences compatible with the canonical trivial fibrations. In any other class of equivalences, we will obtain by localizing the gregarious, right? So by adding even more weak equivalences to the class of gregarious. If we want to be even more explicit about what this is saying, we're saying any other such class of equivalences satisfying our agreed assumptions 1 and 2 will fully contain as a subclass the gregarious double equivalences. So this is the sense in which we're saying these are the minimal class of equivalences that we could ever put. So that's how that's what we understand as a full justification about these being canonical, right? These are the smallest class we could take. And in a way, anything else we can build out of these, those are the ones that are going to require the choices. Because then you will be choosing, okay, what else do I want to say is an equivalence? What else do I want to localize? But there are no choices to be made about these being equivalences for any possible model structure. All right, so I do want to mention this is not the only evidence in favor of the gregarious ones as the canonical ones. So as I said, when Campbell introduced this notion, he already had this idea in mind, and the justification he provides is that the gregarious model structure is the model structure on double categories having the canonical trivial fibrations in which all the objects are fibrant. So this is yet another point in favor of the canonicity of this model structure. And after I first gave this talk a couple months, maybe not even a couple, maybe a month or so ago, Tom Leinster came up with a beautiful paper that gives another point in favor of gregarious. He shows that two double categories are gregariously double equivalent precisely if you can find a span between them where both legs of the span are canonical trivial fibrations. So interestingly, in his paper, there's no homotopy theory at all. So Leinster gives like a completely categorical justification of why these should be the canonical ones. Maybe I think this is pretty neat because we used homotopy theory to identify them and make them stand out of the crowd, but there's also an inherently categorical reason why these should be the ones. So I'll say, of course, as we would expect of these as pieces of evidence, why are they championing this notion? It's because both of these situations, both Campbell's explanation and Leinster, mirror the corresponding scenario in CAD and 2CAD. All right. So I think at this point, my first goal of the talk is pretty much satisfied. We were after a notion of canonical equivalence. We are saying we think Campbell's gregarious equivalences should be the one, and hopefully I've sort of convinced you of the truth of that statement. So now I want to pivot into another goal, but I think it might be a good time to pause for questions because we are going to take a slightly different direction from now on.
Sure. Thanks so far, Mara. That's great, very clear. Is there a tri-categorical explanation of these equivalences? Like, say you gave the homotopical, a couple different homotopical ones and the spanny one from Leinster. Do you know whether there's a tri-category of double categories whose internal bi-equivalences are the gregarious equivalences?
Yeah, so that starts to get a little tricky.
Yeah.
And the reason is that even so if you think about it, even in the two category you can form from double categories that I mentioned a while ago, I was saying you can do double categories, double functors, horizontal natural transformations. There's already a bias in that two category because I could just as well take vertical natural transformation. So there's a choice that I'm making in that two category as well. So that's kind of a tricky thing about the notion of natural transformation, that you have two notions now for double functors. So I think more than a tri-category, you would need like an n-fold thing
Yeah.
that could accommodate all of these things. There was actually a really, really fascinating talk at CT this year, and the slides should be up, where they explained how double categories don't fit into any higher structure that you would naively guess they should. So they explain like what kind of n-fold structure precisely you would need to use to contain really unbiased, all of the data. And I do expect that if you take something like that, you should be able to get an internal notion. That's something that I'm hoping to do soon with some undergraduate students, but it's not as easy as it seems at a first glance. But definitely there should be a notion like that would extract some description, like instead of objects, morphisms, squares, you would want to extract the description in terms of there exists some like inverse double functor and some kind of higher natural transformations relating the composites to the identity. So absolutely, yeah, that's the kind of description that would yield. Yeah,
Great. Yeah, very helpful.
I fully expect that will be true.
Right. It makes sense. Thank you.
All right, so coming back to our new goal from now on, now we have kind of settled the canonical case, but we still have all of these other classes of equivalences, all these other model structures lying around. So what Moser, Verdu, and I set out to do was to further understand all of these. So there's a bunch of these model structures on double cats. In fact, the three of us have done a bit of work over the last 5 years or so on constructing even more examples of model structures that try to accommodate different purposes. So it should be possible, just like from a foundational point of view, it should be possible to create a picture that allows you to understand all of these in some common ground. Like, what's the relation between them? What do they have in common? Maybe there's things that we shouldn't need to prove ad hoc or construct ad hoc for each specific application we have in mind, but rather can we think of like a unifying perspective that brings all of these under its umbrella? So that was our next goal. And we managed to prove, of course, as I said a little while ago, so this is a theorem that I'm repeating from some slides ago, that any model structure on double categories with the canonical trivial fibrations is a Gauss field localization of the gregarious one. So this is a result we already have. So in a way, it's already achieving this goal that I'm saying of giving a unifying perspective. What do they all have in common? How could I construct all of these? This theorem tells you you can construct all of them by localizing. That's it. But the thing is that that really only solves the problem, I would say, in theory, which is super nice as a category theorist. I think that's really neat. But in practice, this notion of Gauss field localization is a little bit wild. Like it's not so easy to work with. It's not so easy to understand. You can imagine when you localize, you can be creating new things that are slightly out of your control. So then you need to go out and characterize and find everything that you localize. So of course, there's been lots of tools in the homotopy theory community to try to understand these Gauss field localizations. This is one of our most important tools for constructing model structures. But still, if you think of it from the point of view of like, well, as a double category theorist, if tomorrow I want to construct a model structure and I have these properties in mind, how would I do this? The Gauss field localization process is most likely not going to be the route that you're going to want to take. So while this theorem answers this in theory, we are hoping for something that's a bit more user-friendly. So something that gives you more concrete tools for like, okay, here's the type of model structure you would want to construct. Here's the properties of it that you have in mind or the applications that you have in mind. When you sit down, what do you have to do? So this is what we're after. And an important fact that we're going to use to try to give this user-friendly recipe is to notice that if you know the class of trivial fibrations and the fibrant objects, that completely determines the model structure. So this is a completely generic model structure fact, has nothing to do with double categories. In any model structure, we said there's lots of pieces of data lying around, but two of those pieces of data, the trivial fibrations and the fibrant objects, completely determine the model structure in the sense that if you give me a class of trivial fibrations and a class of fibrant objects, there either exists a unique model structure with those classes or no model structures at all. So the reason why this fact is particularly handy to us is that the trivial fibrations are already determined. We want to study the model structures with the canonical trivial fibrations. So we already assume we know what these are. In a way, half of the structure is predetermined. So really, all of these different examples and applications are just going to come from different choices of fibrant objects. That's what we're saying right here. So you can come up with a class of fibrant objects, and they will either exist a model structure for you or they won't be. So what we're trying to give now is a way to cook up the model structure in the case when they do exist. So I know that I haven't defined fibrant objects for you. This is not the most friendly model structure talk. But maybe just to say kind of a few words about what these even mean. The fibrant objects in your model structure are the nicely behaved ones, let's say. They're the important objects for you that you're trying to capture. So think, for instance, if you have R modules, the fibrant objects will be the projective ones, right? So they're the ones that have a better behavior, but at the same time, you can kind of understand the whole theory if you understand the fibrant objects. So this is what we're trying to figure out here. If you have a special class of double categories in mind, maybe for some applications that you want to do, the double categories that you want to use need to have a bunch of properties in terms of their horizontal morphisms or in terms of the squares that they have, yada, yada, yada. Look at your class of special double categories. We're going to try to cook up a homotopy theory for those. So that's what I mean. That's what you should keep in mind when I say fibrant objects, a special class of double categories. All right, so what's our user-friendly recipe? Step one, as a user, you're going to come, you're going to sit down, and you're going to pick your desired class of fibrant objects. So you choose for whatever application you're interested in, who are the nice double categories that you should be featuring. Okay. So step two, now come the steps that you need to take to make sure that there is a model structure that has them. Step two is find a set of cofibrations with cofibrant domain such that a double category is fibrant according to your definition of fibrant. This is what you picked in item 1. Precisely if you look at the double functor to the terminal double category, and that double functor has the right lifting property with respect to every map in the set J. So the way that this typically works is like I described a little while ago with the generating cofibrations. You have your class of desired fibrant objects, and you're going to try to describe their properties as explicitly as you humanly can. Like they have this on objects, they have this on horizontal morphism, they have this on vertical morphism, right? And so on. And then you're going to try to extract for each of those properties, how can you encode them by lifting against some functor. And those are the functors that are going to populate your set J. This is how this will go in practice. For every single example that we have wanted to work with, this has been pretty okay to handle, actually. So we've found this to not be bad at all. And I'm going to talk a little bit about examples in the last few minutes. All right, so that's step 2. List the properties of your fibrant objects and identify a set of functors whose lifting properties capture all of these properties. And finally, step 3, last step, you need to check something. So this is what you need to prove as a user. You need to check that every gregarious fibration between what you chose as fibrant objects has the right lifting property with respect to these maps that you selected. So I want to point out a couple things about this check. The first thing is that the description of the gregarious fibrations, which I haven't given to you today, is just as explicit as any other class of maps that we've seen. It's completely described in terms of what it does to objects, to both kinds of maps, and to squares. So working with gregarious fibrations is not bad at all. If you combine this understanding with the understanding that you personally have of your class of fibrant objects, this turns out to not be so bad. Especially because in every example that we have come across, the set J is very finite. Like, think 5 maps or something like this. So it's not, it's typically not a massive list of lifting properties that you need to check. It's just a handful. I also want to point out that this check that you have to do, that every gregarious fibration between fibrant objects has a right lifting property with a specific set of maps. This is in contrast to what you would need to prove without a theorem like this, which is you would need to go to the axioms of a model structure. These are like 5 axioms in the classical version. And you would need to verify a bunch of things that have nothing to do with gregarious fibrations at all. You would need to find factorizations for things. You would need to prove some closure properties. And that's typically an enormous amount of effort. So this recipe boils it down to really, this is the absolute minimal you would ever have to check. And if you're able to verify this, then we prove that you will construct a model structure with the canonical trivial fibrations and with your desired class of fibrant objects. So this is enough to prove the existence of the homotopy theory that you're after. In particular, combined with the knowledge that these are, by our previous theorem, Bell's field localizations, we know that the weak equivalences between your fibrant objects are still going to be the gregarious ones. So that class didn't grow at all. All right, and finally, we're able to prove that this recipe not only does it guarantee that your chosen class works, but it's exhaustive in the sense that any combinatorial model, any nice model structure with the canonical trivial fibrations will always arise from this recipe. So it's not missing out on any others. They always arise from some clever choice of fibrant objects and some clever choice of the set J. All right, so I want to very quickly outline some examples that we've had. So maybe I'll populate this table all at once. So these are some examples that we were able to construct using our recipe by, as we said, choosing different classes of fibrant objects and then checking that the conditions hold. So we can both recover some previously existing model structures in the literature. Those are the ones that have the orange citations. But we were also able to cook up some new model structures, and each of these, depending on the fibrant objects, will capture different homotopy theories. So for instance, we have homotopy theory in double categories that captures exactly that of two categories using the embedding of two categories into double categories. So now if you want to study two categories, you can study them in two cat, or you can look at them as living inside the double categories and study them using this homotopy theory. We similarly have a new homotopy theory for two groupoids that kind of plays a similar role. So I'll conclude here. I'll leave a picture up with the lattice of all of these model structures that were already in the literature, along with our new examples, and all of the relations that hold between them. And I'll thank you for your time.
So thanks, Maru. That was an exceptionally clear and elegant talk. So thanks a lot. And also perfectly timed. So we've got some time for more questions. If anyone in the audience wants to raise their hand. Yes, Andreas.
I hope I'm unmuted. Yes, I enjoyed the talk very much. This last picture that's up on the screen now raises a question for set theorists like me. So you've got quite a number of these possible model category structures there. And these are either examples from the literature or the ones that you found. How many are there altogether? I mean, there are at least this many. They're most the proper class, but can one say anything more precise about that?
No, we can't. We actually thought about that a little bit, and it's not. We couldn't even find a good way to approach that question. Like that question came up in our team as well, but it's not clear. So if you allow me to just show you the table and you look for a second, what are all of the fibrant objects that are determining these new examples that I show in the lattice after? They're codifying different properties about horizontal and vertical morphisms. For instance, do both of those have companions always? Maybe only one of those has a companion. Maybe they have a companion in a conjoint. Maybe only the equivalences have a companion. So, you can imagine a bunch of combinations. So I'm sure that if we were talking about codifying model structures whose fibrant objects can be expressed in terms of somebody having companions and or conjoints, we could possibly count all of them and figure out which include into which. But of course, you can come up with classes of fibrant objects that are not expressed in terms of companions and conjoints and are just like arbitrary properties that they can have. And we don't really know how we could count those. The best we could do was figure out, as some of our results imply, that the gregarious one is always going to be initial in this lattice, in the sense that, it's going to map to all of them and they're all going to be cooked up by localizing it. And right at the bottom of this picture, you see this double cat CTR that stands for contractible. So that is the terminal one. So we found like the first one whose weak equivalences are contained in everyone. And we found the last one, which will be a localization of every other one, but we don't really know how to control how many things live in between. Yeah.
Thank you.
Any other questions?
Sure. Would you mind fleshing out that property you described on the model category of equipments? I think H-equip. What do you mean by equivalence and variance of formal category theory there?
Oh, right. So this is in one of my co-authors. This is in Paula's thesis, and actually her paper came out on the arXiv really recently. She uses equipments and this model structure on equipments to talk about formal category theory in the sense of, instead of looking specifically at categories or two categories or double categories, what if you just look at formally some category theory what are some properties about that that will be invariance under equivalence? It's a lot more on the logic side, so I'm sure that I'm not doing justice to her results. But that's what I meant by this. But if this is piquing your interest, I would prompt you to look at her paper. It's really cool.
Thanks.
you.
Yeah, I had a question. It seemed as if you were mainly talking about strict double categories. I'm not sure if that's the case.
It is.
Okay, does I mean, a lot of nice double categories are pseudo, right? They're weak in one direction. Like, do you expect this work to carry over straightforwardly to that, or is that a whole new world of challenges? Yeah.
We're not entirely sure.
Yeah.
I think that's a direction in which we want to go really soon. Like not
Mhm.
only the pseudo, but also there's this paper by Mike Schulman that came out recently too that does like virtual in both directions. So we're
Yeah.
be like super excited to see.
Yeah,
That's
yeah.
obviously way further down the line.
Right.
We would we would also like to understand how much of this can pass to like virtual double categories where you don't have composites.
Mhm.
I think if you were to order them, the pseudo will be the case that we have the best hope our results would translate. I think it's fair to say maybe we need to develop some new techniques, but I would expect that they work out. The other two are like we don't really have good guesses. However, the thing is that for pseudo, we would probably need to identify a different class of equivalence. Like it's not all that clear because over here it was all very symmetric and we used that
Yeah.
quite strongly.
Okay.
So it's not super clear what answer you would end up at the end, but we do hope to be able to adapt our techniques to say something about the pseudo case. Yeah.
Yeah. Yeah. I mean, so perhaps first of all, I'll go ahead and stop the live stream here since we're approaching the end of the hour. Um, uh, but if you have time and people, we can perhaps continue a little longer in the discussion. Uh,